The last thing we're going to look at in this lecture is a proof of the empirical rule. Let's recall what the empirical rule stated. It says that about 68% of the data values will lie within one standard deviation of the mean. Okay, that's, let's see, right here. Okay, this is one standard deviation of the mean. We have x bar, meaning the mean, right in the center. X bar minus s is a standard deviation below the mean. X bar plus s is a standard deviation above the mean. So what is this z-score? You should say that that z-score is -1 and this z-score is +1. So approximately 68% of the data values fall within one standard deviation right here. 95% fall within 2 standard deviations, and almost all of the data, 99 to 100%, fall within 3 standard deviations. We now know enough about the normal distribution to prove that this is true, because earlier in the semester I asked you to just memorize these values, 68, 95, and 99 to 100%. Now I'm going to prove to you where they come from. So, what are the lower and upper z-scores that correspond to x bar minus s and x bar plus s? So I had just stated this earlier. If z equals 0 in the center, x bar minus s is 1 and negative 1 and x bar plus s is 1. So the lower z-score is -1 and the upper z-score is 1. When we go to use normal CDF with a lower limit of -1 and an upper limit of 1, we'll show that the proportion of area is approximately 68%. So let's go to the calculator. Second, DISTR, normal CDF. We're going to do a lower z-score of -1, an upper z-score of +1, mean of 0, standard deviation of 1, and press paste. Okay, 0.6826, etc., which is approximately 68%. So the empirical rule comes from this derivation of the area under the bell curve between z equal -1 and z equal +1. Okay, let's take a look at the area within 2 standard deviations. The empirical rule stated that 95% of the data values lie within 2 standard deviations of the mean. What are the lower and upper z-scores that correspond to x bar minus 2s, which is x bar, the mean, minus 2 standard deviations, and the mean plus 2 standard deviations? What are the upper and lower z-scores? You should say z equal -2, right here, z equal -2, and z equal +2. So if we go to our calculator using z equal -2 as the lower limit and z equal +2 as the upper limit, let's prove the empirical rule. .9544, or approximately 95%, and this is what the rule states. Okay, the last part of the rule states that almost all of the data, almost 99 to 100% of the data values, will lie within 3 standard deviations of the mean. So what are the lower and upper z-scores that correspond to x bar minus 3s, the mean minus 3 standard deviations, and the mean plus 3 standard deviations? That's here and here. The z-scores that we're talking about are z equal -3 and z equal +3. So if we go to our calculator and use a lower limit of -3, and an upper limit of positive 3. .9973, which is almost 100%. So we do have to account for the outliers that could happen past -3 and past +3. So we say that approximately all, about 99 to 100% of the data values fall within 3 standard deviations of the mean. So that is the proof of the empirical rule. Hopefully that rule makes a little bit more sense now that we could demonstrate its values through the normal CDF function on our calculator. Okay, so that lecture, or this lecture, is all about calculating areas under the bell curve between two z-scores. Eventually, we're going to be using raw scores. So once you're familiar with using z-scores, we're going to graduate to using raw scores, which are basically values for continuous variables, because the bell curve is going to be used to model continuous variables. The area under the bell curve is the probability that an event can occur. So what's the probability between two values under the bell curve? It would be the area under the bell curve between those two values. Okay, if you have any questions on this, please send me an email or post the question in the discussion forum. I'll see you at the next lecture.